Welcome to week 6 of Data 650. This week we will be studying the Hadoop Distributed File System or HDFS. In the following weeks we will be looking at MapReduce, which is the basic way to compute with big data, and also other applications of HDFS such as distributed databases like HBase. So the focus for the next 2 or 3 weeks is going to be on the Hadoop ecosystem. You already heard in your first week that this is the era of big data. That means several petabytes of data. The basic question is, how do we store this data and manipulate and compute? The solution is the Hadoop distributed file system. So the HDFS is the file system that allows you to ingest very large amounts of data and compute with the data. So these are some of the main features of HDFS. It has been designed from the beginning to run on low-cost commodity hardware, and because low-cost commodity hardware is cheap, it also has a high probability of failure. So again, from the beginning, the HDFS was designed to be highly fault tolerant. And of course, when you have large volumes of data, you naturally expect long latencies, but that is just not going to be helpful. So HDFS, again from the beginning, has been designed to provide high throughput for very large datasets, and also to provide streaming access to the file system. Okay, so those are sort of the main requirements that the designer and the architect of the HDFS, Doug Cutting, had in mind when he started working in around 2003 on developing HDFS. So immediately these requirements tell you what kind of assumptions were made in architecting HDFS. As I already mentioned, hardware failure is going to be the norm. There are always going to be a certain amount of PCs or hard disks or switches that fail in a large cluster. We need streaming access to the data, and therefore he chose a simple coherency model. Okay, so what that means is, when you ingest a large file into HDFS, you close it and you are done with that file. In other words, you cannot edit parts of that file. You cannot insert into parts of the file. The only thing that you are allowed to do is to grow the file by appending to the end. Okay, but once a file is ingested into HDFS, it is ready for access, it is ready for computation, but it cannot be edited. So that is the simple coherency model that the architects of HDFS came up with in order to satisfy the other conditions, constraints that they saw were required for a successful distributed file system. The second key observation they made is that it's going to be faster and cheaper to move the execution code to the data rather than to ship these large amounts, the large volumes of data to a central CPU for computations. In other words, computations are going to happen locally where data is stored. So that was the second key assumption or realization that they had, in order to satisfy all the other properties that they desired for HDFS. And finally, of course, because the goal was to use low commodity hardware, they decided that the HDFS file system should be completely portable across any heterogeneous hardware and software platform. So now let's dwell into some of the details of HDFS system. So the development of distributed file systems started earnestly around 2003. There was a project called Nudge. It was a web crawler, open source web crawler system that was being developed by Doug Cutting and colleagues, and they needed a distributed file system that could manage several million web pages. And I think the initial demonstration was done on 100 million pages. So that was the origin of the Hadoop distributed file system. While that work was going on, Google also published their Google file system paper that came around 2005 2006, as you can see here. And a little later, Google also published the Bigtable details. They've been using Bigtable for a long time, and that developed that gave rise to the HBase project, which is a columnar distributed system. It was not until 2011 that the first version Hadoop 1.0 was released. So it took a while. There were lots of intermediate releases, of course, and many companies were using them. But Hadoop 1.0 was released in 2011. And then I think around 2014 we had version 2.0, and currently I believe the stable version is Hadoop 2.9.0, but Hadoop 3.0 has also been released. Okay, now you can see this development here along this column, along the first column, but simultaneously a lot of other related technologies were also maturing. As you can see here, Google was slightly ahead in time of the Apache projects. And also, Google had developed a container system called Borg, uh, which, um, which was used to manage the resources on its huge cluster. So the Borg was essentially, the system essentially divided their data center into cells, and each cell contained about 10,000 nodes. And the Borg was a master slave configuration, and it used the resources in a distributed manner, but was at the same time able to contain and isolate different applications, and they could simultaneously run both batch processes and long running batch processes and short running user originated processes. So that technology has now developed into Kubernetes, and simultaneously the Linux ARM has resulted in the development of Docker. Some of you may have used Docker. Now, the a very significant development is that in Hadoop 2.2, you can actually run Docker containers. Okay, so we will talk about this in little more detail later. But from 1.0 to 2.2, there was a lot of internal development work, and now HDFS can support container. What that essentially means is that you have a distributed file system running on a very large cluster, but you can create hermetic, airtight containers for running specific applications on the on the distributed file system. So that was a major development in Hadoop 2.2. A little later, Spark was released, and it was it's a distributed computational engine. It was designed to run on Hadoop. It can also be a standalone system, but uh, most enterprises run Spark on Hadoop, and of course we will be looking at Apache Spark in detail in the coming weeks. And now, of course, we have Hadoop 3.0, as I said, and again, it has much more sophisticated resource management compared to Hadoop 1.0. So when I say HDFS, I need to be very clear which version of HDFS I'm talking about, because the internal details of how the system works vary a lot from version to version. So to give you an idea, here is version 1.0, a simple HDFS with the MapReduce version 1. And then you see Yarn, which is actually an acronym for yet another resource manager or node. And Yarn was developed and introduced in version 2.0, and this also enabled HDFS to support containers. And as you can see here, you got MapReduce version 2 and Spark and a lot of other applications running on Yarn, supported by Yarn. And you can containerize each one of them, and you can provision for different users. um, It'll be like a virtual machine that has that gives you some HDFS storage and gives you all the goodness that comes with the Yarn resource manager, and maybe Spark and some APIs for running machine learning algorithms in Spark and things like that, all put inside a container and given to you as a virtual machine. Okay, so today, in this lecture, we are going to focus solely on Hadoop 1.0, and the goal is to try to understand all the basic concepts, the fundamentals of how files are written into HDFS, files are read from HDFS, how to configure HDFS, and how to actually use it. Okay, so once you learn that, then we will move on to in the coming weeks studying MapReduce as well as Yarn and other parts of the Hadoop ecosystem like HBase. Okay, so today's focus is going to be on Hadoop 1.0, the basic version of an HDFS. And this is a schematic of what a Hadoop cluster physically looks like. You got several racks, and the racks host a lot of data nodes, and they may also host other nodes such as the name node or the secondary name node. And of course, there is a switch that connects all the PCs, all the nodes internally and to the other racks externally. Okay, and typically you have several hundreds of these racks, and the switches are shown here schematically. there is generally an integration and aggregation of the switches, okay, across the racks. So just look at this for a few seconds and make sure you understand how the cluster is physically configured. Okay, and here are a couple of photos of data centers, one from around 2013, and you can actually see a lot of PCs hooked up together in racks, just steel racks. On the right side, you see a more modern data center. You can see you don't have whole PCs, but if you look closely, you can see that there are blade servers, and they are all nicely internally connected together, and you can see the cooling tubes going into the racks, and so it is a much more efficient configuration and more purposefully designed configuration. Okay, so that's how things have evolved in the past 5 to 6 years. Okay, so this is the basic HDFS architecture. You can go to the Apache website and you will essentially see this kind of an architecture explained on the user guide or on the architecture guide. Okay, so always when you have questions, you can go back to the Apache website for Hadoop and look through the documentation. But this is the simplest way to describe the HDFS architecture. As you can see, it is a master-slave architecture. The name node is the master server, and there are a number of data nodes. These are the slaves. The name node functions as the manager of the file system namespace. So it has metadata about how each file is stored across the data nodes. And we will get into the details a little later. The data nodes usually just store the data, and they are hosted on a rack, and they manage the files that are stored within them. Okay, the name node keeps track of how a file is distributed across the data nodes, and the data nodes manage the files that are within each data node locally. Okay, so one important concept is block size. When you try to store a file in HDFS, you do not store it in its entirety on a data node. Instead, the file is broken up into blocks, and usually the block sizes that are preferred are 128 MB or 256 MB, depending on how big your cluster is and how big your data nodes are. Okay, so files are first chunked into blocks of about 256 MB, and they are distributed across the nodes. Now each block is stored 3 times across the cluster. In other words, there are 3 instances or 3 copies of each block in the HDFS system. Okay, all of this helps with fault tolerance. As we will see later on, you know, if you lose a bunch of data nodes, or you use a whole rack or a whole switch, then you should be able to use the duplicate copies and restore the lost file system, the lost files. Okay, and the next important concept in the HDFS architecture is rack awareness. So the name node not only knows which block of which file is on which data node, but it also knows which data nodes are on which rack, okay, and how many racks there are. And again, we will see that this helps both with fault tolerance and to ensure high throughput. Okay, so remember that was another main criterion, main requirement for a distributed file system, high throughput. So fault tolerance and high throughput are ensured by chunking the files into blocks, replicating them, and then storing them across the cluster in a rack-aware manner. And the data nodes keep sending heartbeats periodically. They keep broadcasting to the name node that they are alive. If the name node does not receive a heartbeat for a certain period of time, then it assumes that the data node has died, and it will first try to replicate the all the data that was on the data that were on that node to the other nodes. Okay, it will distribute those data to the other nodes, and then it will stop sending further requests or further data to that data node. Okay, so this is again how fault tolerance is achieved. We will go into the details soon. Okay, um, and finally you have a secondary name node. Now that is not a standby for the name node. It is what it is uh, what it does is it ensures checkpoints on the metadata. So the name node contains metadata. As I said before, it captures and stores all the details of where every block of every file is stored, and it and also the duplicates, the replicas of those blocks, and then in addition it also stores information about which data nodes are on which rack. So all that information keeps growing as you ingest more and more data into HDFS. So at some point you need to checkpoint the metadata so that if the name node fails, you can restore it. Okay. So, however, the secondary name node is not a failover for the name node. All it does is periodically asks a name node for the metadata, and then it checkpoints them. Okay, and we will see how that happens. Okay, so that's the overall architecture of the HDFS system. Now let's look into the details of what happens when you try to write a file into HDFS. Okay, so the green thingy here is your client, maybe your laptop or your desktop. You may be running a secure shell, and it is connected to the cluster. Okay, from this client you're telling HDFS to put some data, let's say file.txt. Okay, and the file.txt will be chunked up into 3 blocks. Let's say each block is 256 MB or something like that. So the client first talks to the name node and says, I have so much data to store. And the name node then tells the client where that data can be stored. In other words, on which data nodes the blocks can be pushed to. And the client then directly sends those blocks to those data nodes. Okay, it's very simple, right? Um, we will see that there are other complications later on, but that is the simple write operation. So the first thing that happens, you can see here, everything is sequenced. The client requests for metadata of the input text, and the input text has, let's say, 250 MB and the block size is 128. Then it is broken into one block of size 128 MB and another of 112 MB. And so the name node says use these data nodes. Okay, so put block 1 at data node 1, 3 and 4, and then put block 2 into data node 2, 3 and 4, and the client executes all the write operations, all those write operations. Okay, so that's how write. Now reading again happens in a similar way. Let's say the client is running some map reduce task, some process. You have taken the files and done some computations with them, and the results are stored in a results.txt. So now the client says, I want to access results.txt. So the name node says, okay, there are three blocks. Block A has these three replicas. The first replica is on data node 1, second is on data node 5, third is on data node 6, and so on. The client then picks the first data node for each block and gets the data from those data nodes directly, okay, and sequentially, actually, so that you have the right order and you have the file in its integrity. If it does not receive a block from the first data node that it tries, it will move on to the next one. Okay, so that's how the read operations are sequenced. Okay, so more details of rack awareness. You can see from here just a metadata file. It says rack 1 has all these data nodes, rack 2 has all these data nodes, and so on. Okay, so let's assume that this switch fails. The switch on the rack 9 fails. Then we got to know all the data stored on that rack. All right, so the name node then schedules a whole bunch of um, read and write operations so that this data can be replicated. Now, when it does it, how will it replicate the data? Okay, let's think about this. We said we want high throughput and fault tolerance. Okay, now if you want fault tolerance, then you need to distribute the data as much as possible. You don't want to put, let's say if a file has three blocks A, B, C, you don't want to put all the three blocks on one switch. Okay, because because when the switch fails, or the rack fails, you lose all the three blocks. But what about the replicas? Okay, how about we store ABC, okay, the first version of ABC on rack 1, the second version of ABC on rack 2, and so on. Well, in that case, if one rack fails, then yeah, you still have the data available in the other rack. But let's say if those two racks are connected together by a switch and that switch fails. So what will happen then? So you need to distribute not only across different racks but also across different switches. Okay, so that is the true rack awareness is knowing how to distribute the replicas of blocks to ensure that whether rack failures or switch failures, do not completely erase all copies of each block. Okay, so that is, so rack awareness goes beyond just storing those data. Now, so why wouldn't we just, randomly pick each replica of each block and then just distribute it as widely as possible? Well, then uh, your read latencies are going to be very, very high, and your computations are going to slow down because you'll have to access data. We will see this, look into it in more detail when we do when we study MapReduce next week. But once all the computations are done and you want to bring the results together, then you have to go across racks and across switches. So locality ensures high throughput, okay, low latency reads and low latency writes. So those two are conflicting requirements. Okay, so you should know that those two are conflicting requirements. High throughput can be ensured if you cluster all the blocks into one rack, but that is not good for fault tolerance. Okay, and we'll see later, all of this is set up a very simple manner in configuration. All right, now that we know what rack awareness is, let's go back and look at how HDFS actually writes a file. So the name node says, okay, go put this file in data nodes 1, 5, and 6. And what the client does is actually first prepares the data node. So he says, are you ready to write? And it says that to data node 1, which then communicates with data node 5 across the switch, and then data node 5 communicates with data node 6 within the rack, and then you get back an acknowledged signal from data node 6, and then from data node 5 to data node 1 and back to the client, and finally the client is ready to actually write the data. Okay, so that's how you ensure that the nodes that were named by the name node are actually alive and ready to be returned to. Okay, and this ensures, of course, as I said, locality of data. When you have the largest chunk of possible data required for a computation on a single rack, then the computation is going to happen faster, especially the reduce operations are going to be faster. Okay, all right, so that is how the failure of that's how rack awareness is used. Now, how do we handle when a data node fails? As I already mentioned, the data nodes send heartbeats, and every 10th heartbeat actually contains a lot of information about all the blocks that are stored inside the data node. So that's called a block report. So if the name node does not uh, it does not receive the heartbeat for a while, it assumes that the data node is dead, and whenever it receives the block report, it rebuilds the metadata file, and then when it knows that the data node has died, it tries to replicate all the data that were on that node to the other surviving nodes. Okay, and you can imagine that this is going to happen quite frequently, and there's going to be an avalanche of read and write operations during replications. Let's say there are 10 racks on a switch, okay, and each rack has, let's say, 10 servers. So you got 100 servers with, let's say, 1 terabyte capacity each. That's a lot of data to be, if the whole switch fails, that's a lot of data to be recovered and written. So this is again a very important factor to consider. Okay, you need to know how frequent or how soon a data node needs to be replicated, and again, that is a configurable parameter that can be set in one of the config files I will show you later on. Okay, so yeah, this is what I described just now. You know that data node 3 is dead. So, and you know that it was on rack 5. So now take A and C and distribute it to node 8, for example. Okay, so um, some more details about the secondary name node. As I said, it is not a failover for the name node. It is simply a device that checkpoints the file system metadata. So it usually connects every hour or so. By default, you can see the parameters I've listed here. One is DFS name node checkpoint period, and you can set this parameter to 1 hour. It is set to 1 hour by default. You can change it if you want. These are all in different configuration files. And there is something called the checkpoint transactions, and that is set to 1 million by default. Now, if you have a very high throughput system and you have very intense usage, then you may exceed more than 1 million transactions. You may exceed 1 million transactions well within an hour. And that's gonna build up the size of the metadata file, so you wanna immediately checkpoint. So that is the purpose of this parameter. Okay, so I think we are essentially done. I'm going to give you some, we have looked into the basic architecture of the HDFS system. We know how fault tolerance is achieved. We know how high throughput can be achieved. We know how read and write operations are done. And I just want to be a little bit more concrete and give you some more details that will leave you with a more concrete picture of HDFS. Okay, so how do let's see let's pretend that we want to design and install a Hadoop system and then use it. Okay, so what are the steps? Of course, you just go download the tar file, and you can uncompress it, and you edit the shell script. Because HDFS is written in Java, it's very important that you let HDFS know where your Java installation is. So that's the only information you are providing to the shell file. And then you run this command to format your name node, and then you start the daemons. Once you start the name node daemon, it will be immediately available on this port. Again, this is the default value. If you want to alter the port number or even the URI, all you have to do is look for etc. Hadoop, and there is the configuration file called core site XML. You go edit the value and put in whatever port number you want. Okay, so it's as simple as that. It's you download it, uncompress it, edit a couple of files, then format the name node and start the name node and the data node daemons. Okay, if you're trying to run a large cluster, of course it's going to be a little bit more involved, but if you want to run in a standalone mode, then it's going to be fairly simple. Now, the details of the name node that we talked about are all in this configuration file. Okay, so here is the block size, 256 MB. So you can set this. It can be either 256 MB or 128 or whatever you choose. And you need to say where in the local file system you want the name node to store the metadata files. So this is the local file system of the PC on which the name node is running. So say C users, your name, or somewhere, and say, okay, this is where I want all the metadata files to be written. Okay, so that's it's as simple as that. Hadoop. So now, how do you use it? You can get the entire list of HDFS commands by simply typing HDFS DFS, and it'll return, as you can see here, all the different options available. So put is the simple operation where you move, not move, but you put a file into HDFS. Get is again the operation you use to fetch a read from HDFS. Move, okay, move from local means you are running your script, a shell script, on your local laptop or desktop, and you have a file on your local file system that you want to move to HDFS. So you do move from local. So these are very simple Linux like commands. You can copy from local, you can copy to local, and you can concatenate files. Tail is, yeah, here tail gives you the end of a file, okay, and things like that. So these are all, if you have worked with any operating system, you can work with the HDFS, okay. It's that simple. Okay, so one last thing, uh, how do we size the cluster? Okay, let's say you are designing a cluster for your enterprise and they tell you we're gonna have I don't know, 2 or let's say 1 petabyte of data, and we want you to design a cluster to be able to store 1 petabyte of data initially. So this is what you do. Does your system use compression? Okay, if it does not use compression, then the compression ratio is 1. What is the replication factor? It's usually 3. And here is the initial volume of data and compute storage. So you're not just using HDFS to store files, you are actually going to do computations with them. And when you do computations, all the results and the intermediate values are not going to fit in the RAM, and some will leak into the disk space. So we will look into the details when we study MapReduce next week, but for now, you can intuitively see that there will be disk storage required during computation. So this is usually 25%. So 1 minus 0.25, that's 3/4. And so if you have a compression ratio of 1 and a replication factor of 3, the total storage required is 4 times the initial data volume at least. Okay, so that gives you an idea of how big the cluster should be if you want to store, let's say, 1 petabyte of data initially. So you need 4 petabytes of storage. Now you have to estimate the data nodes, so that simply you have to just simply divide this by the number by the storage amount per data node. But again, there is a catch. You don't use the entire capacity of the data node for the storage, because you will also have the HDFS files and other operating system files stored on the on each data node. So you have to allow for that. So eventually you can calculate the total number of data nodes needed. Okay, so this is just an example to give you a concrete feeling for how HDFS functions internally. Okay, so I hope this is useful. Please read all the materials listed, and in the discussion. And I think this Friday we will send out a meeting WebEx notice. We will do another lecture on MapReduce and Yarn, and then one more on HBase in the coming weeks.